Hello, this is Bahar. I'm a member of SAS Center of Excellence. Today I would like to share with you how we at the center attack supply chain management problems through the use of simulation, machine learning, and optimization. This work is joined with the director of SAS Analytics Center of Excellence, Jin Shin Yi, and the product we will be using today to perform most of our task is SAS Simulation Studio. I would like to start with our general approach towards SAS supply chain analytics. First, I will be talking about how we describe the supply chain flow to be modeled through a simulation model. Then, I will be talking about how we actually capture the input data and any uncertainty associated with them. So I'll be referring the first two steps as performing descriptive analytics. Then we are going to be using SAS Simulation Studio, and it will mimic the flow of thousands of products, inventories that may be flowing through the system, and it will produce a large data set which will be composed of supply chain KPI output data. So therefore, by the end of the third step here, we will have performed a supply chain simulation that provides us KPI predictions. And then we are going to be using this supply chain simulation to try different scenarios and ask many questions. And through observations of our results, we are going to be moving towards an optimized supply chain design. And therefore, we will have actually a loop from supply chain optimization towards the supply chain simulation. And this is how our predictive analytics and prescriptive analytics would be connected to each other. First, what I would like to do is to show you the example supply chain flow. Now, we are here going to be talking about how we can actually capture a supply chain network flow using this particular illustration. It is composed of 4 channels: production plants, supply warehouses, mixing centers, and customers, where the demand is originating. And I am using this configuration as an example of what we can do. And I will actually be using a simplified version of this for the preparation. However, if you have a different configuration, then the tool and the approach we are presenting here can also be customized towards your needs. Now, let's just start looking at the flow. So the demand arrives mixing centers and supply warehouses in our example. And then actually we pull the demand from the mixing centers. When the supply warehouse also receives demand, it also meets it and just sends it to the customers. What feeds the system is actually the production plants that produces according to their daily production schedules. Upon completion, they push the finished goods inventory into the supply warehouse, and we consider supply warehouses as being close to the production plants. And mixing centers, this is where we apply the inventory control policy. And this policy determines how often and at what size orders will be received from the supply warehouses so that actually mixing centers can pull inventory from the supply warehouses. So this is a high-level description of the supply chain flow, which is the starting point to our supply chain analytics. And we incur a series of costs actually through this flow. They include production costs, transportation costs, holding inventory at supply warehouses and mixing centers, and also back ordering costs. In this example, we are going to assume that we are going to be actually using demand backlooking approach. However, if there is a step of losing the customer order, if it is not available and sitting in an inventory, we can definitely capture that as well. And then at the very bottom, you see our key performance indicators that we are going to be using in this presentation. They are, therefore, the total cost and the supply chain fill rate. We are going to be also looking at what is the fill rate by supply warehouse and by mixing center. The distinguishing feature of our tool that we are using, which is SAS Simulation Studio, is that it enables us to obtain a scalable simulation. So the logic that we are going to be building here is going to be independent of the number of production plants, warehouses, and mixing centers, as well as customers and products. So therefore, the model we are describing here is going to be flexible, scalable, and it will also be data-driven. And here's a simple example that I will be using. While we can have any number of manufacturing plants, warehouses, mixing centers, and products in our supply chain flow, here is an illustration of having two manufacturing plants with 20 different products. We have 10 products associated with each manufacturing plant, 2 warehouses closely located to the manufacturing plants, and then 5 mixing centers. And we also make assumptions about where these manufacturing plants and supply warehouses may be located at Cincinnati, Analyst, because in this particular case, and where the mixing centers are located. These locations are important because they are going to be helping us determine what the transportation time is, as well as the transportation cost from one location to another as the products are flowing through the supply chain. Now, let's just look at, for example, product 10 here. According to our input data, product 10 is manufacturing in plant 1 in Cincinnati. It is sent to the supply warehouse. And when there is a replenishment order received from the mixing centers, which is in Oklahoma City and which is actually mixing center 3, it is pushed into that particular inventory. And then it's finally sent to the customer when we arrive at shipment time. Now, here you see the list of simulation input data that we need next. So far, we have talked about the configuration. Now, let's look at the data set contents one by one. Let's start with initial inventory. This basically tells us the number of units of inventory that we will have in the very beginning of our simulation by location. And here we see that on the upper left-hand side that we have the most initial inventory sitting in Pittsburgh in our mixing center too. And we can actually compare it alternatively as well. And again, we see that this is where we carry the most of the inventory. And for the simulation, we need more granular information. So we actually need the decomposition of this total inventory of 300 units by product. And this is what we are seeing. And again, when looked at the by product, this is the location, mixing center 2, where we carry most of the initial inventory. After we have the information about initial inventory, the next step is to obtain the information about our production plan. So this is in an hourly basis and what each production line in each plant produces. And we see that production line 5 in plant 1 makes most of the production. And of course, we have this information by product as well. And here you see how each day we add to the weekly cumulative production. We also assume uncertainty around production times. In this very simple example, we assume that each production order actually takes an average of 4 hours, and we assume a 50% variation around it. And then when we actually send the fresh goods inventory from the production plants to the supply warehouses, we assume an average of 3 hours transportation time, and we also assume a 50% variation around it. So these are examples of the type of production plan data we need as we are actually describing and building the first simulation model. The next step is the customer order information. So these are the demands that are going to be received at supply warehouses and mixing centers. What we are going to do first is show you the results of our deterministic demand case. And we need to define, and this is why we have them all fixed at 1,000 units on a weekly basis. And we need this information by location, and we also need it by product. And again, we see that Pittsburgh is where we are receiving most of the customer demand as well as by product. After the specification of the customer order, we need to also specify the transportation details. We need how long it takes to go from one location to another. Let's take our mixing center 3 as an example. So we are going to be transporting goods with trucks from the supply warehouses we have located in Cincinnati and Las Vegas. And we see that actually this is where we incur most of the production time that are shown here in hours. However, we also need information about the detailed trucks that are traveling on those routes. And here you see the number of trucks we can have on these routes. And we also add even more information about the capacity of each truck, the minimum load capacity each truck requires. So you can, again, just treat your trucks as individual resources and provide more detailed information. So this is also a great tool for you to understand the impact of your fleet, transportation fleet decisions on your overall supply chain performance. And finally, here we have the supply chain inventory control parameters. Here we are going to keep it simple. We have 20 different products that are stored across 5 different mixing centers, and we need an inventory control parameter set for each one of them that determines how often we are going to review the inventory, and with about we are going to make the ordering. And here we are using the periodic inventory policy specified by reorder point and order up to level. We are basically checking the daily inventory level for each product at each location of the mixing center. And if the inventory level, for example, for product 1 at mixing center 1 is less than 60 units, then we place the replenishment order. And we are going to define it in a way that we would like to have an 100 unit inventory at this location. So this replenishment order goes to the supply warehouse to pull inventory. So there are 2 types of levers on this illustration in our example. These are the reorder points and the order up to levels. If you would think of this as an optimization problem, these levers would be corresponding to examples of decision variables you would have in your system. There are 2 different data sets we have left to specify. Supply chain cost parameters is the first one, and production yield and forecast error are the second. Here we specify our unit production cost, transportation cost, cost of placing a replenishment order, the unit back order cost, as well as the unit cost of holding inventory at supply warehouses and mixing centers. And under the assumption of 60 units of reorder point at our supply mixing center 1 for product 1 and an order up to level of 150 units and 100% production yield and no forecast error. Here you see our example of the total cost decomposition into the components that are displayed above, and this is as a function of the time window. And this is going to be basically making our total cost that we would like to minimize. Therefore, so far we have talked about a supply chain whose total cost we would like to minimize. And as an example, we are focusing on how we can actually manage the inventory at the mixing centers. And we have two decision variables or controls or levers that we can play with to minimize the total cost. And those levers are the reorder point and order up to level. Now we have all the information we need to build our supply chain model in SAS Simulation Studio. We have the supply chain flow and all the input data in place. The next step is to determine the randomness in some of these data sets. Here's an example. For example, production time. We said that the average production time is going to be 4 hours, but we are going to have 50% variation around it. So on the x-axis in the first plot, you see all the possible values production time can take place in a production plant, and y-axis indicates how likely it is to attain each of these production times. And then we have a similar risk profile for the transportation time. So this is the way, these are the plots we are going to be using to capture the randomness in the inputs. Then we are going to specify the levers we have in the system, and we are going to use them as we design the simulation experiments. So you can actually have a wide variety of levers that you can play with to move towards a good system of supply chain design. Here we are going to be using our reorder points and order up to levels, and then we are going to be execute the simulation and obtain the risk profile of the supply chain key performance indicators. So we are not going to be only computing a single value about what the supply chain fluid and what the supply chain total cost can be. We are going to be capture the risk in those predictions, and that is the beauty of this tool. It allows you to understand and be informed about the risk your supply chain is exposed to. So the key benefits of this tool is that this is scalable, data-driven, and flexible, and we can, at SAS Analytics Center of Excellence, customize our supply chain simulations to your needs. And as a result, we can help you to experiment in the virtual lab that we create so that you can assess the impact of operational policy and strategic investment decisions on your overall supply chain performance. At the same time, you will be equipped with the power to predict your supply chain KPIs, because the supply chain simulation is a large supply chain KPI data generation. Not only you would obtain your performance measures, but you can track any production order, you can track any inventory, you can track any customer order in this particular tool. And furthermore, you can quantify the risk because you will have a large data set. So you can apply all your statistical, powerful tools to understand and quantify the risk. And once you can do that, actually, you can experiment with a large number of scenarios and move towards identifying a better design for your supply chain. And here is an example here where we look at supply chain service levels and supply warehouse service levels, mixing center service levels, and we also quantify the average and standard deviation of the total cost. And this is where we have an example of 40 reorder points, 106 order up to levels. What happens actually when we increase 40 to a larger number where you would place orders more often and in larger quantities? we see that your system improves. What if we have demand uncertainty in our system? Then demand uncertainty adds more variation. So it degrades the performance. So we can now use this tool to find effective tools to fight against the uncertainty and the risk we are exposed in the system. So as a result, we have a supply chain simulation capability that enables the creation of scalable, data-driven, and flexible supply chains. It further integrates with SAS visual data mining and machine learning libraries for you to more effectively actually perform scenario analysis and optimization of your system so you can get closer to real-time decision enablement. Thank you.